Hello, my name is Rob Reynolds. Welcome to Chapter 5, our first section, learning about antiderivatives. And today we're going to undo a derivative. And this is the symbol for an antiderivative. It's called the integral. And just as you know, if I have a function, I can find the derivative, y prime, by multiplying 4 times the 3 and then decreasing the exponent by 1. Well, today we're going to integrate 12x cubed, and instead of decreasing the exponent, when you integrate, we're going to increase the exponent and divide by it. So here, when you took the derivative, we multiplied by the exponent. Now you're going to increase the exponent, and whatever that exponent is, that's what you're going to divide by. And notice you get right back to where we started. So that's what antiderivatives do. They undo the derivative. So here's the definition of the antiderivative, and we could talk a little bit about the domain. This says, hey, we don't really know, back in our very first example, if we took the derivative of 3y to the fourth plus 5, we would get the same thing, 12x cubed. But if we took the derivative of 3x to the fourth plus 6, you would still get the exact same thing. So they're saying there's some constant out here. And we don't really know if that constant is a plus 5 or a plus 6 or a plus 7 or a plus 8. But when you take the derivative, we're going to end up with some plus c. There could be a constant out there. So we don't know what that plus c is. So we'll just remember when you take the integral, there could be some constant term out there. And we'll just say plus c because we don't know what that is. So if you take the derivative of an integral, it undoes the function, and you just write back to f at x. It's kind of like taking x plus 5 minus 5 and getting back to x, or taking x multiplying by 5 and dividing by 5. They are inverses of each other, and to inverse the derivative, you take the antiderivative and you get right back to the function. Likewise, the integral of a function, or the integral of a derivative, is back to the function. But we'll say, remember, plus c plus some constant. Here's all the rules, basic integration rules. And the last one that I just explained with you is x to the increase the exponent by 1, and then whatever that is, we'll just divide by that. And remember, we're going to say plus c. I want to highlight here something that you cannot do. If you have the sum, yep, you can break it up. If you have the difference, you can break it up. What's not here is the integral of a product. This does not equal the integral of a times the integral of b like you might want it to. That's a big noper, and I won't show that to you. This is important. If you have a constant, you can pop it out, but we did that for derivatives as well. We knew that the derivative of a log function is 1 over x. So now, guess what? We're going to integrate 1 over x, and we'll get the log function. So undoing. So let's practice a couple. If you haven't already, go to Blackboard and download the worksheet that's there. It's a blank copy of this, so you can work these problems along with me. If you wanted to think about this first problem as x to the 0, that might give you a hint about what to do with the exponent. So if it's a 0, we're going to increase that to a 1, divide by the 1, I'll write it, and you have your first answer, 1/2 x plus c. Likewise here, if this is a 1, then we know that we have an x plus c, because the derivative of x just gives me the 1, and this guy is going to be negative 5x plus c. Here are the author's solutions. I seldom do this constant rule, but I'll show it to you because it is helpful later, but I wouldn't have done it for this problem. I just would have increased this 1 to a 2, divided by the 2, and there's my final answer. Whereas if you want to write that as 3/2 x squared plus c, you can. But they're going to say you could pop that out and then increase this 1 to a 2 and then divide by it, and it gives you the same answer. But didn't see a reason to pop out the 3 in this case. But sometimes that is helpful. Sometimes it's also very helpful to do some quick rewrites. You want to rewrite 1 over x cubed because we don't have a low d high minus high d low rule like we do for products. You'll want to rewrite that as an exponent and then increase that -3. Now remember, when you increase a -3, then it goes to a -2, and then divide by it, and then rewrite the final solution. So a quick rewrite for the square root function is to change it into an exponent. And when you increase 1/2 by 1, you get 3/2 and divide by it, and then don't leave the answer like that. Do a quick little rewrite. When you divide by 2/3, that's like multiplying by the reciprocal. Excuse me, when you divide by 3/2, that's like multiplying by the reciprocal. So that's how they got this 2/3 out front. When you see a sum, you can use the integral rule, this integral of x plus the integral of 2, and the integral of x says increase this to 2, divide by it, I'll write it as 1/2 plus 2x plus c. Again, I won't write it, but I'm going to think about integrating each one of these. So I'll start with the first one. Increase this 4 to a 5, divide by it, increase the 2 to a 3, and divide by it, and increase the 1 to a 2 and divide by it, plus c. We'll see the author's solutions. Good. 1/2 plus 2x plus c. I think that's what I had. Yep. And this last one. Good. To do a rewrite for radicals, I showed you an example of that already. This is a 1/2. Then you could break that up. X over x to the 1/2 minus 1 over x to the 1/2. Let's continue simplifying. So I haven't taken the integral of this thing yet. The integral of this is a 2/2 minus, so rewrite the base and subtract 1/2. And then let's write this as a -1/2. And then I'm going to increase the exponent. So x to the 3/2 divide by 3/2, which is a 2/3. Minus x to the 1/2, because when I add 1 to -1/2, I get a positive 1/2, and then divide by 1/2, which is like multiplying by the reciprocal, plus c. Here's the author's worked out solutions. Looks like they got the same thing I did, but then they did one last step, was to change that back into radicals. So let's pull out this 2/3 and the square root of x, which is literally like dividing each term by 2/3 x to the 1/2, 2/3 x to the 1/2. So this is kind of nice that it cancels here. So what's left is x to the 3/2 divided by x to the 1/2. You rewrite the base and subtract. 3/2 minus 1/2 is 2/2, or just x. Minus, and then it's 2 divided by 2/3, which is 2 times 3/2, which is just 3. And then plus c. That turns out pretty nice. That's what they had for the final solution. Did I? Yeah, I changed that back into a radical form. So I could see that there was, each form had a 1/2. The reason why you do that is because this makes it really easy to find critical values. So I can see there's a critical value here now of x equals 3. So if you can put these things in factored form, that makes it easier. Here I'm going to show you a graph or two about the many different types of integrations you could have. Because we don't know what the c is, any one of these c's could work. So if given a derivative and you find the function, remember that function has many, many, many different y-intercepts going through this. But I think you would agree with me, there's only one curve that goes through the point 2,4. So if they give you a point 2,4, we could actually solve for that c value. Remember, if they give you the point 2,4, they really give you an x and a y. So this is a y, so that you could say 4 is equal to 2 squared minus 2 plus c. And you could actually solve that then for c. And it looks like c turns out to be -2. Let's practice one. So here we're going to integrate 2x minus 2 and get, since this is a 1, and divide by it. Well, I'll write it 2 divided by 2, which is just x squared minus 2x plus c, and there's the y value. So they're saying f of x equals y, so x equals 1, y equals 2, and I'm going to plug that in right here. So 2 is equal to 1 squared minus 2 times 1 plus c, which is 2 equals 1 minus 2 plus c. I'll keep working down. Negative 1 plus c, and add 1 to both sides and get c equals 3. So I'll write the final equation, x squared minus 2x plus 3 for my function. And here's worked out solutions from the author. You can see they also got the plus 3 because it could be any one of those solutions. And again, all of this is posted on Blackboard, so you can check that as well. Application just means I have to do some reading. Here's a general equation. V sub O is your velocity. This is your initial height, S at O. So if you read through this, it tells you that the initial height is 80, and right here, and the initial velocity is 64, so we know S prime 0, that's at time 0, is 64. And there's one more thing. Acceleration due to gravity is negative 32 feet per second. So we know that the second derivative is negative 32. So if I'm going to go back and write the first derivative function, I'll say, well, the first derivative is really the integral of the second derivative, which is negative 32 dt. So I'm doing s at time. And if I integrate this, I'll get negative 32t. That doesn't look like negative 32t. Negative 32t plus some constant. We'll call it c sub 1 for my derivative. And it tells me, though, that this constant is really 64. Because if I plug in a 0, I'll get c is 64. So I'm going to write this function as s prime t equals negative 32t plus 64. Next, I want to find the function, so I'm going to integrate that. So I'll say s at t is the integral of negative 32t plus 64, because when I integrate the derivative, I'll get the function. And the integral of this is t squared, divide 32 and get the negative 16 plus 64t plus some other constant. We'll call it c sub 2. You can just keep calling it c if you want, but that's the function. And then we're going to use this s sub 0 at time 0. We have 80. So if I plug in an 80 right here, and let this be 0, 0, because 0 times anything is 0, I'll get c sub 2. The second constant is 80. So writing the equation, s at t is equal to negative 16t squared plus 64t plus 80. I can factor out a negative 16 from that. T squared minus 4t minus 5, and I think I can factor that. T plus 1, t minus 5, set that equal to 0, and find out that time has to be 5 because it doesn't make sense for it to be negative 1. So the ball's in the air for 5 seconds. Let's see what the author has to say about this. So good. Coming up with the derivative is 64, that's given. Also, due to gravity, you had to come up with the gravitation pull of the Earth. They integrated this. Of course, this is posted on Blackboard as well if you'd like to see. They factored it, and then they made their conclusions the ball's in the air for 5 seconds. Let's try one more example. They're giving you marginal cost, and they say, let's integrate marginal cost to go find me the cost. So that doesn't really look like an integration symbol at all. So we'll integrate this to be 32x minus 0.04 x squared divided by 2. I'll simplify that. Plus c. I might get this c mixed up with this c, so I don't know if it would make sense or not, but it's some constant. You might want to let the constant be k so we don't get this cost mixed up with our constant. Or you could say c sub 2. I don't know. Maybe just avoid c altogether because c stands for cost this time. So it's saying that it produces $50 for every 1 unit. So we know c sub 1 is 50 when x equals 1 unit. So let's plug that in. 50 equals 32 times 1 minus, this is 0.02 times 1 plus k. And then go ahead and solve for k. And I think k will turn out to be $18.02 if you do the number crunching there. So then we could go ahead and write the equation. C is equal to 32x minus 0.02 x squared plus 1802. $18.02. So what did they say? Find the total cost when producing 200 units. So C sub 200 says every time you see an x, plug in 200. 200 squared plus $18.02. And again, number crunch this, and I think C sub 200 will be very close, rounding to the nearest penny, to $5,618.02. You can enjoy the number crunching. So again, oh good, the author used a k as well for their constant, and they got 18.2. That's good. And then what did they do? Yeah, they got the same thing. They let the cost, let x be 200 and solve for c. So here are the definitions or the rules that we've been using. Remember, this works for addition, not for multiplication. It works for subtraction, but not multiplication. And frankly, not division. The integral of a divided by b does not equal the integral of a divided by the integral of b. We use other strategies to integrate products and quotients. But this is the most powerful thing. If this is the only thing that you learn, increase the exponent and then divide by it. That's how you integrate. I hope this video was helpful.